My name is Rene Williams. I am assistant professor at the Molecular Photonics Group at the University of Amsterdam. And today we will talk about perovskites on silicon tandem solar cells. We will talk about the composition and the components, and we will see how supramolecular self-assembly on the interfacial recombination layer can lead to a functional whole transporting monolayer. Perovskite silicon tandem cells. If we combine these perovskite materials with standard silicon solar wafers, we can absorb the blue light with the perovskite and the red part in the near infrared with the silicon. In July, people reported 33.7%, almost 10% higher than the standard silicon module. This is from Berlin, from the Helmholtz Center. Above 30%, people have reported that in various ways. You also see that it is a very complex material. The silicon layer is extremely thick relative to the other components. You have all kinds of very, very thin layers, less than 100 nanometers. The perovskite here, and they form a stack with different components, with different functions. So we can discuss the composition, what perovskite is ideal, additives, we have the 2D perovskite interface, and a recombination layer. You have to use it. So currently we are at 33.7% for these tandems. In a period that the silicon development has basically stopped, that silicon has been at 26 over the last 5 years. In this period, the tandem cells with perovskites, they have really skyrocketed. You have a high band gap material and a low band gap material. This one absorbs the blue part of the spectrum. The other one absorbs the red part of the spectrum. The light has to go through the top cell and arrive at the bottom cell. That is the general idea of tandem cells. You can do it with any kinds of combinations of semiconductors. And this is what they do for perovskite. So you can see that up until like 750, the perovskite does the work. And above that, the silicon does the work. So depending on the wavelength, you have a quantum efficiency that can be pretty high. So it's a combination of two materials, a tandem solar cell. You heard something about Shockley-Queisser limit. So for silicon, it's 29. The real theoretical limit is 33.7. And for silicon, of course, the band gap is basically the energy difference between the valence band and the conduction band. That is how you can look at it. For a single junction, we have a certain limit. For a tandem cell, the limit is different. And it depends on what you combine. For silicon, it has been stable for many years now, the records. Silicon is an indirect band gap semiconductor. So that implies that you need the p doping and the n doping. So you need to put some phosphor in one layer, some boron in the other, and in that way make a p-n junction. It works excellent, and of course silicon is dominating the market. Perovskites are a direct band gap semiconductor, so you don't need to do the trick with this doping. You can combine any types of materials. If you can choose all the properties, you can get up to 45%. Silicon perovskite, the limit is 44.3, and if you use organic materials, the limit is slightly lower. But for the combination of silicon with perovskite, this is the ideal band gap of silicon perovskite. And in principle, if you go to this limit, you can get 2.3 volts and about 21.6 milliamps. So then you get the theoretical maximum efficiency. You already know about the perovskite structure. So the materials are similar, but they tune the composition for the tandem cells. And that means that they especially put in cesium and bromomidinium. So we can tune the band gap of the perovskite layer. If you use metal ammonium lead triodide, you are at 1.5 electron volts. Now, if you use the bromide, then the energy gap is larger. So if you make a mixture, you can tune the energy of the band gap. And you can do that also for the bromomidinium and also with effect of the cesium. You can take it all together. And in that way, you can try to tune it to the optimum. There are different types of silicon wafers that you can use. Here they call this the homojunction, which is basically just silicon n-doped and p-doped. But there's also silicon heterojunction. So that is more complex. At the bottom layer, you have a thin layer of amorphous silicon, either n-doped or p-doped at both sides. Most people in this field, they use a silicon heterojunction as the bottom cell. And you also see that they can make them structured. So there's a structuring of the lower layer here. And they have more absorption in the near infrared part. That is one of the advantages. Another thing that you have to take into account is the terminal. Ideally, you have what they call a homolytic system. So you have the two layers on top with a very thin layer in between, and you make it one device. But you can also just take a device here, a device there, and stack them on top of each other. So that is a 4-terminal. Then you just put two separate devices on top of each other. The monolithic 2-terminal devices is the most common or the most interesting, but it has a limitation. It has a limitation because you need to have current matching. If you take a 4-terminal or a 3-terminal device, it doesn't really depend on the band gap. The maximum efficiency that you can get doesn't really depend on the band gap. For the 2-terminal, you really have to be at the optimum. So you have to be at 1.7 electron volt. Otherwise, your efficiency drops because the two layers, they are interconnected. They're interconnected by this recombination layer. We will get to that. If you look at the compositions that have been used a lot, then especially the combination of cesium and formamidinium, that is the most promising, that gives the highest efficiency. Cesium formamidinium combination is higher for both the configurations. There's problems. One of them is phase segregation, that you get bromo and iodo rich domains. The ions, they move in the material and they segregate. You also get vacancies. If you have strain in the material, an ion is kicked out. Here, there's lots of vacancies for the iodine. So here, an iodine is just missing. And you can prevent that with additives, adding molecules that can improve it by using certain tricks. For instance, if I2 is formed, it helps to reduce it back to I-. You can imagine that it can interact with lead. This is also an additive that is used to do the same trick. You can substitute the Br- for Br3-. You basically improve the binding. So you have less defects if you take this additive. You can use the alkyl ammonium additive. So you use bulky alkyl ammonium molecules. This would be a bulk crystal, just a normal perovskite structure. But in between the crystals, there, these alkyl ammonium molecules, they end up there. And they can interact. So they form the interface between two grains. And they can do that with forming these 2-dimensional structures. So you can imagine that you have a big crystal at one side, and in between you have a layer of these 2-dimensional perovskite structures with these longer tail alkyl ammonium molecules. So in that way, you can change the material between the crystals. So you can tune that by using alkyl ammonium additives. Butyl ammonium has been used, this thiophene molecule, but especially this phenylethyl ammonium additive. So that gives the 2-dimensional perovskites in between the crystals. And people have been able to visualize that. Here you see a layer of all kinds of crystals next to each other. If you zoom in at a certain region, here you see these little layers. This is a 10 nanometer scale. In between two bigger crystals, there's a 2-dimensional structure that is created by the addition of these alkyl ammonium additives. So it's like a special interface on the nanoscale between two crystals. Altogether, these are the chemicals. It is a semiconductor business, but you use chemicals. Lead, you use iodide. This is the main component that has been used from the beginning. Metal ammonium, it's actually not that good. Formamidinium is much better, more stable also. And these are the alkyl ammonium additives that people use. So you can see that they try to tune the structure of this interface to make it better, to change the alkyl ammonium structure and thereby have better performance and better interaction of the crystals. Here we have some additives that do the reduction of the I2 to I-. And here we have some anionic additives, formates, the anion of formic acid, but also I3- and Br3-. They can take the place of the halogen, of the I- and reduce the amount of defects. They interact better and they block the creation of defect states. So these are the typical chemicals that you can think about. But also these ones. So this is this monolayer that we discussed. Another one is piperazinium that they use as the electron transport layer. They can make high efficiency devices, silicon with perovskite on top of it. But in between, We have supramolecular chemistry. We have a self-assembled monolayer of a particular molecule with a phosphonate group and an electron donor. So here is this molecule in between all these stacks. You can also see that the structures that they use, the silicon, it has a pyramid structure. So that is a general trick in the silicon field, that you make black silicon, you make a pyramid structure that absorbs the light better. You get reflections, internal reflections. But here we have our monolayer on indium tin oxide. So this is a monomolecular layer of this molecule. It's a self-assembled monolayer. So like we saw for our alkyl thiols on gold, and it transports the whole. So it transports positive charges. Here, they use the same molecule. They also have a self-assembled monolayer of this carbazole derivative, paper from the Berlin group. You also see that they make all kinds of devices, thin ones, thick ones. You get a range of efficiencies, and they certify just one of them. So this is a choice. They choose a particular device. They send it to the organization that can do the certified efficiency. It is a rather small thing. From maybe 100 devices, they choose one to get the records. It's all about world records. There's also a patent on this molecule, especially since various groups use it as the whole transport layer. So here you have the whole structure. You can try to look at the components, and you see that they're all very, very thin layers on the nanoscale. But on the bottom, we have the silicon. It's extremely thick relative to the rest. It's 280 micrometer. But there's a textured back. This means we have a pyramid structure on the back of the silicon. Here we have the perovskite. You see, it is containing cesium from a medium, some iodo, some bromo, some chloro. They actually don't know exactly how much is in there, about 600 nanometer thick. On top, we have this piperazinium iodide. This molecule, as the iodo salt, it's an ionic liquid and is good at transporting electrons. It is a donor acceptor system. This part is electron rich, this part is electron poor. Piperazinium iodide, it is the electron transport layer on top of the perovskite. And there we have C60 on top of it, then some tin oxide, some other layers, some anti-reflective materials. On the bottom, there we have this self-assembled monolayer of this carbazole molecule on top of a very, very thin layer of transparent conductive oxide, indium oxide in this case. So you see, we have a multi-layered stack, very, very thin layers, less than 100 nanometers. It's nanotechnology. And we even have a self-assembled monolayer of this molecule. One more thing, that is the recombination layer. Here we have the silicon, here we have the perovskite. In between, we also have a recombination layer. What does that do? It's 20 nanometer thick, and this is what it does. Here's the light. Here we have the top cell. With light, we create charges. We create an electron hole pair, a plus and a minus. But in the bottom cell, we do the same. So we also create a plus and a minus. Negative charges, they go one way. The positive charges go the other way, but these, in between, they meet. So they have to recombine. So you have a special oxide layer where the plus and the minus recombine. And that means there have to be equal amounts of positive and negative charges that meet there. So that's the current matching. There has to be equal amount of positive and negative charges for them to recombine efficiently. You'll also call it a tunnel junction, a recombination junction. So here we have the plus and the minus that recombine, and the other ones, they form, the amps of the cell is similar to a single junction. But the voltage is higher. So here we have a typical representation of charges moving through bands. They're tilted because of the operation, because of the charge buildup in the system. And we have a voltage. So for these tandems, the situation is more complex. We have a charge here, we have a charge there, but also in the other cell. So this charge, it needs to recombine with that one in this recombination junction. Thereby, you can make a higher voltage. These charges, they have to recombine in this very, very thin layer. That's the idea. And by doing that, you can create a higher voltage. When you put two batteries on top of each other, they're in series. So that voltage is added. Another thing is the texturing. So it's pyramid. It can be pretty big, but it can also be pretty small. You can imagine that if you have a textured top of silicon, it's very difficult to deposit the perovskite. So if you want to do spin coating on a bumpy surface, it's not that easy. So maybe you have to do other tricks, evaporation, but you can also play with the texturing. So here we have nanotexturing. They have made sinusoidal surface structure on the silicon, much smaller than these pyramids that are general in the silicon field. So only a couple hundred nanometers of this surface. So it is easier to deposit your perovskite layer. So we use nanotexturing. With lithography, we can make nanotextured silicon surfaces. We can control the dimensions, and that influences the interaction or the deposition of the perovskite. We have nanotextures. We can use them at both sides. And this represents the problems that they have with the big pyramid. So if you have the big structuring, it can happen that your pyramids of the silicon that you use stick out of the material. So they don't function. They use special mixtures of salts to get the best deposition with spin coating. This is another approach next to this nanostructuring. If you look at the composition of some increasing efficiencies, there's a clear, if you look at it, you see that there's basically between 5 and 10% of cesium. There's not a lot of metal ammonium, and there's not a lot of bromo. But more chloro, it does help. So they incorporate CO- as much as possible. This is the general trend. For composition, there you see the same. This is the cesium that's only there for 5 to 10%. You also see that the main gain is the voltage. So as you go from the lower to the top, you're getting to almost 2 volts, starting from 1.7. So the development in the field is leading to better voltages. The currents, they are not changing a lot. They're already like 20.5. So that means for the current, we're pretty close to the theoretical maximum. But for the voltage, there's still a lot to gain, like 200 millivolts. And that's huge. And one more thing. So if you take the best values from what has been reported, the best voltage, the best current, and the best fill factor, you can anticipate 34.2%. So that should be attainable. It can be done. Perovskite silicon tandem cells. And the message is, we're using supramolecular chemistry. We're using a self-assembled monolayer as the whole transport material on top of the recombination layer. And you can also think about improving composition. Then you have to think about these aspects. You're also using alkyl ammonium additives. That's like forming a very thin molecular layer on the crystals. And you can think about nanotexturing.